Dear ladies and gentlemen, welcome to this station of the booth. Let me right at the beginning ask you a very provocative question. Are you interested in lowering your TCO, shortening your time to market, or integrating or interworking with vertical architectures? If so, welcome to this booth. Due to several new challenges, OTTs, WeChat, WhatsApp, Fiber, the telco business has changed. It has become more aggressive. One of the reactions was going to virtualization. Virtualization brings a little bit more complexity and cannot apply it by one day, one night. You always will have some physical, some virtual, some cloud-native architecture. You will have wireless environment, you will have wireline environment. All this can be managed with one solution. The world's first ZTE end-to-end service orchestration architecture, which is ready for commercialization, able to be deployed, and able to manage a full network infrastructure as a service. We have used a 5G architecture to show how easy such an architecture system can manage your network end-to-end. The ZTE Cloud Studio is an end-to-end service orchestration architecture. But to be honest, it is more. It allows you and your maintenance team to get a complete overview of your network. You see the system status, the alarm status of your network, how is the health. You see the application status below with your blueprint architecture, with your application status on VNFs, on PNFs, on network services and slices. You see your virtualized resource utilization on CPU, on memory, on disk. And you have an overview about the used physical environment where this system runs on. In addition, you can get a total overview on geographical level of your deployment. What has been realized here is one central DC, one edge DC for 5G RAN, and one edge DC for GPON. All of this has been interconnected with an SDN network, allowing to cross-communicate dynamically between the sites. Each edge DC can be zoomed in. You see the details of this edge DC, allowing really to focus on your health status for this specific one, on your application status, on your physical infrastructure and your resource utilization. The same can be done for the transmission network in between. For each of the slices, you have a detailed view on your SDN transmission network, allowing you to focus on analysis of your transmission links. The system also gives you the opportunity to design your network slices by yourself. With predefined VNFs, which are integrated into the system, which can be ZTE or third party, you can build your own network structure, depending on your data center infrastructure, depending on your local infrastructure, and on your service you would like to deploy. Each of the network slices which is built can be enhanced, can be modified, and can be optimized depending on your needs. The SLAs, the services, can directly be integrated into the tool to make for scaling, for optimization, for migration, the optimal use case happen. The system is allowed also to develop and to do a test on the infrastructure itself. It means it verifies what has been designed is correct. It does a verification on security, it does a verification on resources, it does a verification on configuration, and it does a verification on the service itself. If the test is successfully completed, the system can be deployed. And this deployment can happen in a very short time. What has been designed before, you see here in this architecture. The deployment itself is a matter of seconds. It selects free resources on the environment, it uses the template defined before, imports the template, generates DNS resources, generates the IWF, loads down the software, creates new interlink functions between the VNFs in a site, between the VNFs for 5G and for fixed net, and also within the infrastructure. It connects to the physical network elements, it configures them, it allows the fronthaul initialization, and it cross-connects the service. Within a very, very short time, you can instantiate a full service set like this EMBB. In the monitoring set, you already can see those slices. One of them we already created right now, the EMBB slice. Another one which was pre-created, the RLC slice, is present and is used for monitoring. Let's have now a little bit a look on the slide details. As before, we have generated two slices. One EMBB slice, one URLLC slice. To start with the URLLC slice, we have to take a little bit a look at the 5G architecture. Till now in 2G, 3G and 4G, the sellable goods were volume, gigabyte per month, and were speed, megabit per second. With 5G, a new unique selling point is added, latency. 5G as first technology allows you to control latency, what this slice in detail should show. The slice is locally built here on this infrastructure. It is composed out of an edge DC with hosting a 5G RAN component, a RAN backhaul component which is interconnecting the edge DC with the core, and a central DC which is doing the full 5G core infrastructure. The ZTE Cloud Studio does an end-to-end latency analysis of the system. It identifies which latency appears on which service, it protocols it, it records it to the KPI data for later analysis, and it allows the AI to do triggers based on these analyses. We have to show what latency control means, build an industrial architecture with those 6 robots. Each of those robots is using this network as transmission network. One robot sends to the next robot and to the next robot a command, such as it uses a command set into the core, down to the UPF function, backwards to the next robot, and sums up such as a delay of 40 milliseconds between each of those robots. If we start them, you immediately can see those robots are not synchronous. One after the other raises his arm due to the fact that we have 40 milliseconds delay in between. What you can do now is you can change this delay. You can go to customers who have interest in low latency, like stock exchanges, like banks, like gamers who want to be the first one shooting, and give them an offer for a better, high-quality service. If they agree, you change the latency of the service, you lower it for this specific slice, for this specific demand. The UPF is moved up to the edge DC, resources are added, caches are cleaned, and the robots are running in a smooth direction. The latency you can see on the Cloud Studio is down to 1 millisecond. The robots are synchronous. If a contract has expired, if the latency is no longer required, you can change back the SLA itself. The system automatically adapts itself to the situation, moves back the UPF to the core, releases the resources, and the system is back to the standard value as it has been before. The second 5G network slice, which is realized on this end-to-end service orchestration architecture, is the EMBB slice. It's a little bit more complex as it has one more data center and one more technology to deal with. We have a 5G edge DC, which contained again of a 5G radio infrastructure. We have a backhaul system of this edge DC, which is composed of about 100 megabit link. We have a common central DC, which hosts the 5G core, the new standard conform N3 IWF interface and function, which connects to the OLT, and one CDN network, which is doing the IPTV CDN for this demo. The second edge DC is a GPON XDC. It allows to offer this IPTV service not only to wireless customers, also to wireline customers. With this construction, you have a unified wireless, wireline IPTV service. We directly can enable traffic over this. This means we have 6 pads connected over 5G and 6 pads connected over GPON. All this traffic you see is running over the core. We activated 4 of those pads, so we have 4 streams, all of them 4K, running over the core. The core itself has an integrated KPI usage system, records all the bandwidth on all the interfaces, records the downlink and uplink throughput, and classifies it. This data is used to handle all the KPI infrastructure, to put it into the big data, and to let the AI race on infrastructures. We go up to the next level. We add more streams, in this case 4 more additional streams. This more traffic causes immediately a reaction on the core. The intelligence on the system detects that the traffic has raised and that the infrastructure has to adapt. This adaptation is automatically. This automatic infrastructure adoption leads to the fact of new Docker container infrastructure addings to deal with this latency and traffic demand. One more traffic increase to add 4 more streams leads to another effect. The interfaces between those data centers are 100 megabit interfaces. The traffic which is generated by 6 times 4K videos is far more than 100 megabit, so they raise an alarm. This alarm raises up an infrastructure analysis process which takes into account all the resources you have in the network to get rid of the problem and to deal with this limitation. Because this limitation leads to the fact that the videos don't run anymore in optimal quality. The system proposes an action. This action is distribute UPF CDN. It means to distribute the broadcast point from the core DC, center DC, to the edge DCs, and to get rid of the limitation of the transmission. This distribution is acknowledged now. All the UPF and CDN functions move to the axis. This process is seamless. There is no interrupt on the service. The service is run smoothly again. There is no fraggle able to be seen. The UPF and the CDN is created. The resources on the core systems are released, and the system runs well. Thanks a lot. I hope it was interesting. Enjoy the rest of our booth.